Hello there. In this video, we'll be learning the limits and continuity of logarithmic functions. To start, take note that logarithmic functions are actually continuous on all positive real numbers. So this came from the fact that the domain of logarithmic functions are only positive real values. So that this idea out here came from that idea, from the domain of logarithmic functions. So as you can see, there is quite a common theme on the continuity of these functions with respect to their domains. So given that one, we actually have two nice properties from this one. First, if f is continuous at a point, say A, it follows that the limit of f at that point is just equal to f evaluated at that point. This just came from the definition of continuity at a point. Next, if f is continuous at the limit of a function, say g, at the point A, it follows that the limit of f of g of x at that point is equal to f of the limit of g at that point. So basically, the wordings is quite confusing, but what happens here is that the f out here can be moved outside of the limit. So this can be moved outside of the limit to be here. So this came from the idea or the theorem on composite limits theorem, which we had applied in the past. So you may check that video out in this playlist. So essentially, we can use these two properties of continuity in our study on logarithmic functions. To understand this better, let's have two illustrations. First, if we have a point A and it is positive, it follows that the limit of ln of x, so this is logarithm, the natural logarithm, so basically this is log to the base e of x. As x approaches a, and since we know that a out here, so a here is positive, it follows that what we do is we just plug in a into the logarithm. So we'll have here ln of a. That is by this out here. Let's have this second illustration. Suppose that the limit of g of x as x approaches a exists and is positive. Then take note that the limit of ln of g of x as x approaches a is, observe that g of x out here is positive. That's the key thing out here. This means that we can apply the second property out here, since g of x is positive. So it is in this interval out here, which means that we can apply this, or basically we'll move ln outside of the limit, or that is, we'll have this out here. Simple as that. So these two are just basic illustrations, but later on we'll try out real values in applying these properties. So basically, we connected the bridge between continuity and limits for this part. But to understand and expound on this further, let's talk about logarithmic limits. To understand this better, we need their graphs. So we let f of x be equal to log of x to the base a with a greater than 0 and a not equal to 1. Given this, we'll have two cases. either a is greater than 1 or a is between 0 and 1. For the first case, its graph would look something like this. So it is definitely increasing. For the second case, its graph would look something like this. It is decreasing. So this is just something that we know in the past from logarithmic functions. So why did we show these graphs? Well, that is because we'll try to understand what happens when we go at the bounds, or at the infinity and towards 0 from the right, and towards infinity and 0 from the right out here. It is important to note that we're only dealing with 0 from the right since we don't have any values from the left approaching 0. So the limit out there is immediately does not exist. So we only deal with the limit from the right of 0 in these two cases. So starting with the first limit out here, as x approaches positive infinity, it would be represented by this region out here. So clearly, again, since this one is increasing, it follows that this limit is equal to positive infinity. For the next one, as the value of x approaches 0 from the right, so it will be represented by this part out here. Then it follows that the value of the logarithm is clearly approaching negative infinity. For the next case, this first one, as it goes to positive infinity, it is represented by this out here. Clearly, it approaches negative infinity since again it is decreasing. For the last one, as x approaches 0 from the right, it would be represented by this part out here, which clearly goes to positive infinity. So these are the 4 limits that you need to remember, or if not, you need to have an understanding of the graph, or even in the function only, just understanding what happens as the value increases or as the value goes to the right of 0. So take note of these out here, since now we'll be trying out examples. So we have 3 examples out here which you may try out first on your own. So feel free to pause the video to try these on your own. Okay, good. So let us start with the first example. We have the limit as x approaches 10 of log of x. How do we answer this? Take note that 10 out here is positive, or it is in this region out here, which means that, as we have known earlier, we can simply plug in 10 into the function. So we'll have here log of 10, and take note out here that log represents the common logarithm. So when the base out here isn't present, it is immediately assumed that it is equal to 10. And then take note that 10 out here can be written as 10 raised to 1. For our knowledge on logarithms, so this would cancel out and we'll be left with 1. There. So that answers the first example. As simple as that. It becomes simple since we know that we can just simply plug it in by the continuity of logarithms. So that is the power of continuity. Let's move on to the second example. We have here the limit of ln of x as x approaches negative 7. How do we solve this? Take note that negative 7 out here is negative, or it isn't part of the interval of the positive real values. Which means that if we recall the graph earlier, the case 1, since ln out here can be written as log of e, wherein e out here is greater than 1. So, as we have seen in the graph earlier, this ln of x doesn't have any value on the negative part. This means that the limit out there does not exist, since it wouldn't approach anywhere, since the graph on the left-hand side of the Cartesian plane has no graph, has no logarithms. So it does not exist. To remark this one, take note that as x approaches b, with b being negative, it immediately follows that the limit of log of x, so this can vary, we can have here log with a base a or ln and so on, as long as it is a logarithm. The limit of this logarithm of x as x approaches b, we know that b is negative. If that is the case, it immediately follows that this limit does not exist. So take note of that. And finally, let's have this last example. We have the limit of log of 1 over x as x approaches 0 from the right, and take note that this is of the base 1/2. So how do we answer this one? It's quite hard to see how this would work looking outside, but we can try to look inside first, the limit of 1 over x. So take note that this limit out here, as x approaches 0 from the right, so what we can do out here is we can just simply plug in 0 from the right into the function. So we'll have 1 over 0 from the right, and we know that constant over 0 is just equal to positive infinity. But the key thing out here is that take note that this one is positive, since values from the right of 0 is positive, and 1 is positive as well. So positive over positive will be positive. And given this, since we know the limit inside, we can actually rewrite this limit out here. So we can set y to be equal to 1 over x. And what happens? Observe that as x approaches 0 from the right, y approaches positive infinity. So that is what we have shown out here. Given this, we can rewrite the given limit into the limit as y approaches positive infinity of log of y with the base 1/2. And we can now solve this, since take note that 1/2 out here is less than 1 and greater than 0. So this logarithm out here represents the second case earlier. And since y approaches positive infinity, we have seen earlier that this approaches negative infinity out here. There. So that answers the third example. And these are our examples for this video. I hope you understand this properly, especially the concept on how this works, since the examples are quite basic, but it is important that we know why and how this works. To end this, here's an exercise that you can try to work on. We have here the limit as x approaches positive infinity of ln of 7x cubed minus x squared. So basically, observe that if we plug in infinity immediately out here, we'll have infinity minus infinity. So there's quite a little bit of trick in solving this one, but it is pretty basic if you know how to solve limits of polynomial functions or limits of these functions as x goes to infinity. Yeah, you can work on this one. I think it is solvable. So yeah, that's it. I hope you enjoyed and learned a lot from this video. Feel free to comment down below if you have any suggestions, comments, recommendations, or whatever for this video, this playlist, and this channel in general. So yeah, that's it, and that's all for this video.